Welcome to this video on looking at structural analysis with the FSL tools. My name is Mark Jenkinson and I'll be talking about two main tools in this talk. One is FSL VBM or Voxel-Based Morphometry and the other is SIENA or SIENAX. Both of them are used to analyse the amount of change there is in grey matter within different images, either at a group level or at an individual level. We'll start by looking at voxel-based morphometry. And the idea here is to look specifically at grey matter and how grey matter changes either between two different groups or with a particular factor of interest such as training or exercise. So as I said, it's looking at the grey matter or the grey matter volume, but actually it's a little bit difficult to precisely pin down exactly what it's looking at because it does a couple of stages in the processing which make that harder to interpret but improve the statistical power. So it is useful for looking at a variety of different things. It can be useful for looking at changes in the volume of the grey matter. It will be sensitive to that, but also sensitive to change in the gyrification or the folding pattern of the grey matter. It's useful for looking at correlations with certain factors such as clinical scores, and it can also be used as a way of looking at measuring structural change which might be caused by neurodegeneration and atrophy of other causes, and how that impacts on other kinds of analyses such as fMRI and PET. So there are a number of different situations that we might use it, and it is one of the most widely used tools in order to look at changes in anatomy, although there are other kinds of things which are available. We've already looked at one in the context of the first tool. In another video we're looking at deep grey matter structures specifically, but if we're looking all over the brain or if we're looking at the cortex, there are other things that we can do. We can look at the cortical thickness, particularly for the outer cortex, or we can look at tensor and deformation based morphometry, which are related but different to this. So there are a number of other alternatives. Voxel-based morphometry or VBM is not the only way that we can do these kind of analyses, but it is very, very popular and has been around for some time. And that is probably because it's one of the most statistically powerful tools that we have. When we're actually doing these analyses, we don't have to have any prior assumption on what structures we're interested in, unlike, say, doing a first analysis where you only have certain structures that we can look at. We actually look at the whole brain and we get voxel-wise maps. That's what the voxel-based is all about. We just get a map of the brain and we see wherever the changes happen to be. It's automated, it's relatively quick, and it can localize things which are differences. And it combines two different things together. It combines together registration and segmentation. And that's important because neither of them are typically perfect. And by combining them together, we actually can get the best out of both worlds and have them compensate for each other. And so there is a trade-off that we have by incorporating both things. It makes the interpretation a little bit more difficult, but again, it gives us a little bit more statistical power. So we can compensate for the fact that our nonlinear registration is not going to be perfect by using the segmentation. In terms of the things that we run through, so I'm going to explain how the pipeline works so that you have an idea of the different stages that it goes through. You can understand the outputs that you'll be seeing when you actually run this process, and also understand some of the things that needs to be able to do to your image so that you know what kind of images are reasonable to kind of process. So we're going to describe the optimized protocol, which is what is implemented in FSL VBM, though it's not the first VBM style thing to have been published. So the idea here is that we take an image and we do a brain extraction on that. So that's fairly familiar and that can be done with the tool BET within FSL. And then we do a tissue type segmentation with FAST in order to get the grey matter partial volume estimate or PVE. Then we make a study specific template and we register all of our subjects to that template with nonlinear registration. We do that with the tool FNIRT. We use a study-specific template so that it's actually matched well to the demographics of the population which is being analysed here, because quite often these studies are looking at pathological groups or they're looking at very elderly groups, and they will not match well with our standard MNI 152 template, which typically shows what the young, healthy brain looks like. So we specifically make something which is tailored to that study, and in order to make it fair, if we're doing a group comparison, we want an equal number of subjects from the different groups that comprise this study. So if we're doing patients and controls, we want to make sure that we've got an equal number of patients and controls contributing to making this template. That doesn't mean that we can only analyze those. We can actually analyze everything later on, and it can be in unequal groups for the later analysis. But specifically for building the template, we have to have a subset which is a balanced set from the, in this case, 2 groups that we're doing, but if we had more groups, we would have a balanced number from each of the groups, which constituted our data set. Once we've done that and we've created our template, then we're actually going to take our nonlinear registration, which is what you see between the left-hand image and the right-hand image. It's taking that image and it is matching it to the template that we've just created, the average of this group that went into building the template. And then we're going to do a step which is called modulation, or Jacobian modulation. And that's going to take this image you can see in the middle here and turn it into what you can see on the right-hand side, where what you can actually see is that there's quite a variation in the grayscale. So some of the parts of the grey matter end up darker than other parts. And that's deliberate because that's actually going to tell us about what was present in the original image prior to it getting transformed by the nonlinear registration. I'll talk a little bit more in detail because this is the most complicated step and useful to understand. So here we've just got an easy illustration of what happens if we've got a face, and you can see that this is a distorted version of this face. So we started with the smiley face, and then actually by changing the grid, by doing our nonlinear warp, we could actually turn it into this sort of neutral face. And that has shifted parts of the mouth around, and it's also, you can see there's a great change in the size of one of the eyes. So going from that image to that image, we can perform with a nonlinear registration. But one of the things that you will see is that actually the amount of grey which was in one of the eyes has substantially changed between one image and the other. And we need to take account of that if what we're interested in is volumes of grey matter in our analysis, which is what we're trying to do in VBM. So the idea is that the Jacobian is simply measure of the local amount of volume change. So if we look at our grid squares, we can simply measure the size of those grid squares in 2D here in this example, but it would be in 3D in practice. And the ratio of what that is after registration and before registration represents our Jacobian, which is a local measure of how much the volume has changed, or in this case, area, as we're in 2D. So this is a case where if we look at something in the eye, that eye has changed size dramatically. So the ratio happens to be 3 in this case. If we look at some other area, then it might have actually had to compress or in a different way. And so here it's changed that the factor is 1/3 instead. And in other areas, actually nothing much has changed. So in that case, the Jacobian will be 1. The ratio of the before and after volume would be 1. And we're going to use that local measure of the amount of change in the volume to modulate our grey matter map. And we do that because actually, if we start out with thin grey matter and the nonlinear registration has expanded that grey matter to cover a wider area, then we've lost the information about the fact that there wasn't very much grey matter to begin with. It now looks like there's lots of grey matter in the image which we would have post-registration. So instead, we incorporate this Jacobian information back into that scan, and we would modulate our image so that the amount of grey matter that you would see in an area like this is reduced by actually changing the level of that grayscale. So this partial volume estimate of grey matter, which is what this image represents, is now reduced in that area, so that if we averaged over that area, if we summed up over that area, we would have the same amount of grey matter that we would have measured in the equivalent anatomical area of our original image. So this is sort of trying to undo the fact that the nonlinear registration is able to expand or compress grey matter. We can measure that through the Jacobian and introduce that back into our partial volume. And that way we have a partial volume which represents the amount of grey matter which was present, but is still aligned nicely between all the different subjects, which is an essential thing if we're going to analyse across multiple subjects. So now we've got the alignment from the nonlinear registration, but we've kept our information about how much grey matter was present in the original one. And that's what the modulation step is there to do. The next step that we do is we actually take that modulated map and we smooth that with a Gaussian filter. And so if we put it all together, what we're going to see is that we're going to do a brain extraction, we're going to do a segmentation with FAST to get the grey matter partial volume. We're going to then register that to create a template which is just specific to the study that we're doing, the subjects that we are analysing. Once we've created that template, we're going to register all of our images to that template, and then we're going to modulate them according to that Jacobian that we've measured. Then we're going to smooth them, put them all together and analyse them. Now you can see that the smoothing has got rid of some of the detail, and that's a step that you might wonder why we're doing. And that's actually a step which causes it to be harder to interpret, because unlike what we had before, where we had at each particular point we had a good location, correspondence between the different individuals, we could say how much grey matter partial volume there was there. Now we have a grey matter partial volume which is averaged in an area, because that's what the smoothing is doing. It's giving a local average. So we have a local average of the grey matter, and so you'll often hear it referred to as local grey matter volume or grey matter density. And it just represents the fact that it's not the grey matter precisely at each voxel, but each voxel represents the grey matter in its local region, an average around that voxel. And that's what we're going to analyse. And we do that because it gives us statistical benefits. It compensates partly for a little bit of location error in the registration, but I think the main benefit that we derive from it is really the statistical power that we get by doing some smoothing. Because if you're familiar with how statistics works, smoothing is always beneficial in terms of helping to suppress noise, as long as you don't smooth your signal away. So you need to make sure that the smoothing is local, so that it doesn't smooth an area where we had interesting amount of grey matter change with an area where we didn't have any change, because then we would lose that ability to see the change. So we do a little bit of smoothing in order to help us out. The amount of smoothing is not something which is pre-specified, and we don't know what the right answer is. And so what you will see when you actually run the pipelines is that there are different levels of smoothing which are performed, and then you can look at the different outputs. And that helps you to give an idea of what's consistent. What do you see at all levels of smoothing? But also what might be more optimal. So if you have larger areas, then they're actually going to be more sensitive with larger amounts of smoothing. If you have small areas of change which are interesting and biologically plausible, then doing a large amount of smoothing can get rid of those. So you would probably favour a slightly smaller amount of smoothing. But it gives you an idea of what is consistent there, and then what you might see at the different ones. Each smoothing is valid. No one is more correct than any other, but smaller smoothings will be better and more sensitive to smaller areas of change. Larger smoothings will be better at detecting larger areas. It simply changes the relative sensitivity of the method to different sizes of area. And so it's useful to have a look and really to try and match the amount of smoothing more or less to the size of the change that you're looking at. But there are other considerations, and I would recommend that you read some of the literature on this if you are going to get into this area of doing voxel-based morphometry. Coming back to some of the interpretation, I talked a little bit about that before, but now that you've seen all the various different stages, you'll have a better understanding of what is going on and why it is sensitive to different things. So quite often we're interested in biological processes like this, where there's a thickening or a thinning of the cortex. That's really, what we're interested in terms of atrophy and neurodegeneration. And VBM is definitely sensitive to that. because the amount of grey matter that we see there and the average within this local area, we are going to see that change. But unfortunately, we are also sensitive to other changes. So we're sensitive to errors in the classification or the segmentation or the registration. So if the alignment's not right or the segmentation's not right, then we're going to see differences which are artifactual, which are just due to the fact that those processes didn't work. And that's one of the reasons that you should look at your outputs, look at the intermediate stages of analysis, and make sure that everything is working correctly. But it's also going to be sensitive to changes in biological things which we might not be interested in, such as the gyrification or the folding. So if in one subject there is little folding and in another subject there's a lot of folding, then actually that is going to influence the local amount of grey matter that we're going to see. And so that's something that VBM will be sensitive to. It's a real change in the thing that we're trying to measure, but it's not necessarily an interesting biological change that you might want to know about. But it's good to realize that that's one of the things that could be driving results in VBM. There are also other reasons that things might differ. So we talked about the amount of smoothness that you do, that does have an impact. How you do the nonlinear registration, how you create the template, as in what subjects get included or not, what kind of software package that you do. These all have some impact. And if you want to look at sort of a best practice paper, then this is one of the ones that we would recommend having a look at. That goes into many of the aspects and looks at how much of an impact they have. This is true not just of VBM, but it's been well studied in VBM, so it's good to understand that. And it's something that the community is aware of and reviewers of your papers are likely to be aware of. So you need to understand what the impact could be and how reliable the results are meant to be. But at the same time, it's been around for a long time, it's been heavily used, and it is one of the mainstays of certainly structural analysis. There's also another variant on VBM, which is the longitudinal variant. So everything I've talked about so far has been cross-sectional. And by that I mean that I have one scan per subject. Longitudinal is when I have at least two different scans, typically a baseline and a follow-up scan. And I'm interested in looking at what changes within that subject, which might be as a consequence of some kind of intervention. So it might be an exercise intervention or something like that. And I want to know, how is the grey matter changing in the brain as a consequence of that over time? And in order to do that well, we don't use the cross-sectional tools exactly as they are. We vary the way they are used slightly. And here are a couple of papers which describe how that's done in order to optimize it to look at the change between the baseline and the follow-up scan, because that's the same anatomy with very subtle changes, and we can measure that better and then combine across different subjects later, rather than putting everything in together at once. So if you are interested in doing these kind of longitudinal studies, then it's worth knowing that there are modifications that you need to make to the standard VBM pipeline in order to get the most accurate results. And that's all I want to say about VBM. The other tool that's worth knowing about is SIENA. And SIENA, again, looks at grey matter, and it is used to look at changes in the structure or the anatomy of the brain. The big difference between SIENA and VBM is the fact that VBM is voxel-wise. It makes maps of where the changes are. SIENA just gives you a global estimate. So it gives you a measurement of the amount of grey matter across the whole brain. And then you can see how that changes longitudinally, which is the normal SIENA program, or cross-sectionally, which is SIENAX. And they're both able to measure this global estimate, and from that you can calculate things like rates of atrophy. You might wonder why we are interested in that if we have a tool like VBM which can actually give us maps of where these things are changing. And the answer to that is statistics, is that by averaging across all of the brain and giving a global estimate, we actually do better than we would do at each individual voxel. Each individual voxel is a noisier estimate, and it's harder to reach statistical significance. It's harder to get very accurate measurements at a local level than it is at a global level. So we can benefit statistically by getting global estimates. And that's why SIENA and SIENAX are still used, because they do have that benefit over VBM of looking at very subtle changes, particularly in widespread global atrophy. So SIENA is the longitudinal variant, and there's a whole pipeline that goes along with it. I'm just going to very quickly run you through the main steps, again, so that you're familiar with the kinds of outputs that you're likely to see if you're actually running SIENA. So it's going to do a brain extraction in the same way that we're familiar with, but also with a twist. It also estimates the skull from the brain extraction. And that's important for us to get really sensitive estimates longitudinally, because we can use that skull in order to constrain the scaling when we register the baseline to the follow-up scan. And the reason that we're concerned about the scaling is that scanners can drift in terms of their calibration. And so what you might think is a 1mm voxel that you've asked for might be a 1.01mm voxel, which might not sound that drastic. A 1% change in 1mm is, it's 10 microns. Do I really care? Well, actually you do, because that represents a 1% change in the linear dimension of that voxel, or a 3% change in its volume. And actually the kind of changes that we're looking at measuring in these brain images are typically 0.5% or something like that. They're around the sort of 1% level, sometimes going down even less than that. So we really want to be sensitive to these changes, and that calibration doesn't normally change actually that much. It's really quite stable, but over time it can drift a little bit. And so when you're doing longitudinal imaging on a particular scanner, it's one of the things to be aware of. And that's why we are estimating the skull and trying to use that to help us come up with something which can measure how much that scaling might have changed. We have to use the skull rather than the brain, because actually we're interested in neurodegeneration and atrophy. So that we expect that the brain is changing, and that that's nothing to do with the scanner, that's to do with the actual biology. But we don't think the skull will be changing. However, that then gives us a limitation to how this can be used, because we are making that assumption that the skull is the same, which is fine for adults, as long as they haven't had some kind of brain surgery or traumatic brain injury, but it's not fine for children. So if you're working with children, or if you're working with a surgical population where they've had some neurosurgery, or you're working with a population with traumatic brain injury, this can be a problem. And so that's one of the limitations to be aware of in SIENA. Once we've done that brain extraction, we've got the skull, then we use FLIRT to do a registration. We actually register to a halfway space. That means that the baseline and follow-up are both interpolated into the halfway space. And we do that so that it's even across the baseline and the follow-up. We don't just interpolate one and not the other. So we make sure that we do that, and we get, again, a little bit of extra sensitivity statistically by doing that. Then we estimate the atrophy in a similar way to what we saw in FIRST. We actually do a segmentation just to give us a rough location for the boundary of the brain tissue. So here we're lumping white matter and grey matter in together. And you can see that represented by the red line in 3.1. And then we're going to take normal profiles of the little green line, like we did in FIRST, and sample the intensity across that and look for where that's changing. And then we're going to do that in both the baseline and the follow-up and see where we can measure the point of maximum change in both and how that's shifted from the baseline to the follow-up. By looking for the point of maximum change means that actually we're insensitive to small errors in the segmentation. So we don't rely on that boundary being exactly correct. We're actually looking at the intensities, and we're driving everything off the intensities directly to really find the most accurate point of that boundary between brain tissue and CSF. Then we can encode every point according to whether it has experienced a sort of atrophy or growth, and we will see growth because it's a noisy process. At each point we don't have a really accurate value, but we do get an accurate value once we sum them all together. And we integrate everything in order to get a percentage brain volume change, or a PBVC, which I find hard to say. So this percentage brain volume change is actually the final output. It's a single number, as I said, it's a global estimate, but it is much more accurate as a consequence of having summed up or integrated over the whole brain, much more so than the individual points that we would get looking at each voxel. And so that's what SIENA does. It gives us this percentage brain volume change between baseline and follow-up. And it does that for each subject. If we then want to do an analysis of that across a group, we would put these values, which are just numbers, into a standard statistical package like SPSS. We also have a tool called SIENAX to do the cross-sectional version. And this goes through a number of different processes, but not all the same ones that we had in SIENA. So we again do a brain extraction, we again use the skull, but because we don't have a baseline and a follow-up, we're actually using the skull to match to the skull of our standard template, our MNI. And so we do a registration to standard space, we use the skull for scaling again, so that if the brain has atrophied and is smaller, then that's fine. And we are just going to constrain it with respect to the skull. And so we get our size matching that way. And then we do a little bit of extra tuning for the segmentation. So we get a partial volume segmentation, but we mask out things like eyes and optic nerves a little bit more precisely than when we would a standard fast segmentation. And that just helps us to get a little bit more accuracy again. And finally, we get a normalized brain volume by looking at the segmentation that we had, again, summing grey matter and white matter together in our standard space. So it's normalized because we've looked at it in standard space. We've done the scaling in order to correct for that. And that actual estimate of the normalized brain volume can be quite useful. And actually the scaling that we use to get to there is a very useful covariate that we often use in other structural analyses. And so this normalized brain volume on its own is actually quite a useful thing. And sometimes SIENAX is run just in order to get that. So in summary, we've looked at two different tools for trying to look at changes in structural grey matter within the brain, looking at changes in the anatomy. Voxel-based morphometry combines registration and segmentation to give us voxel-wise maps of grey matter, or the local density, the local volume of the grey matter, because of that smoothing step. We create a study-specific template. We need to make sure that we're balanced between the groups so that we're not favouring one group over the other and we don't have any statistical bias associated with that. We put the spatial smoothing in to help with the stats, although it makes the interpretation more difficult. It's an arbitrary amount of smoothing that we have to do, so you have to choose. And we give you several different options to choose from. And again, having a look at those papers is helpful, and just roughly matching the size of the smoothing, size of the changes that you're interested in is also a useful thing to do. Like in all the kinds of analyses, it's useful to check the different stages of the pipeline, check that they've worked. That's why we explain the different stages, so that you know what to expect and you know what to look for. If anything does go wrong, you will need to identify at what stage there was a problem and then fix it. It may be that the brain extraction needs to be fixed in some way, and that you might have options for doing that. It might be that you need to fix something to do with the registration, and you need to identify where things have gone wrong. And sometimes it's just that there are artifacts in the images and that they can be cleaned up and everything will work from that point. But it's really useful to identify where things have gone wrong, so that you can go in and then fix them if necessary. Many times everything just works fine, but we cannot guarantee it, so it's always critical that you have a look at these. There are also alternatives to VBM, such as looking at cortical thickness within the outer cortex. If you want to do longitudinal, there's a separate pipeline or modifications of the VBM pipeline to do that. And there's also a way of estimating global changes in grey matter, or global amounts of grey matter, using the SIENA or the SIENAX tools for longitudinal cross-sectional studies